Hello, hello, hello. Welcome back to another live stream. It is Thursday, the 6th of November, and today we're going to do another stream going through the skills you need for Oxbridge interview prep. I don't expect anyone to be live because I have given no notice that I'm going live at the time, and it is also 9:45 p.m. Apologies for that. I play the violin, as you can see from that guy back there. Got a concert coming up this week, and so the schedule's been a little bit skewy. But I wanted to keep putting out the videos at the regular one a week for interview prep, just to make sure you guys feel good and ready going into that. So last week we went through graph sketching, everything to do with that. Today I'm planning on going through a different skill, which is derivations. So because Oxbridge interviews don't have calculators in them, they can't rely on your calculation skills. So you're not going to be asked to, unless there's like standard things, like cos of pi over 3, these sorts of things that you should know. Basic computation, yes, that's fair game. But on the whole, they're not going to be asking you to do a huge amount of computation. What they will be getting you to do usually is lots of derivations. So deriving expressions based on your understanding of math or physics. And as in the case with physics in particular, or engineering, making some real-world predictions based on those derivations, and then assessing whether those seem sensible or not. So I'll go through a few of the classics that I've been using with some students. And as usual, sort of looking at the process that I'm going through is going to be the most important thing. Because as always, an interview is a lesson, not a test. So it's not about going in, knowing all the right answers right away. It's about demonstrating a process that they can trust you can get from point A to point B on your own, maybe with a little bit of help. One of the most important things with derivations is to be absolutely rock solid on anything to do with the syllabus. If it doesn't seem that familiar to you, you can drag it into a topic you are familiar with and use your understanding of that topic to try and make some headway. Even if you're wrong, it demonstrates to an interviewer, yeah, I've got the skill to do this. And by the way, even if you're wrong, that's not necessarily something an interviewer holds against you, because they might be thinking instead, if that had been the question, they would have had the skill to do it. So anything you can do to demonstrate what you know and what process you use is a good thing, even if it doesn't immediately get you the answer of the question being asked right away. So with all of that said, let's launch into it. Let me get you over there. And I'm just going to share the Miro whiteboard that a lot of you would get if, for instance, your interview is online. If it's in person, you're going to be working pen to paper. But I think typically online interviews are done on a style of whiteboard like the Miro whiteboard. So that's the one I'm going to use to demonstrate these questions. I think, should I do the window? Yeah, okay, no, we'll just do the whiteboard for now. So the first derivation we're going to go through is a personal favorite of mine, which I started using last year, which is based on a cylinder. So we have a cylinder. No, that's not a cylinder. No, try that again. So we have, that'll do. We'll call that a cylinder. So in the cylinder, we place a piston. Now this piston is it's going to be airtight, so no air can get in or out, but it will be able to move. And so a question might be, what happens when you drop the piston, when you release the piston? And typically you'd say something like, well, I know it's going to have some weight, so I know it's going to fall. But as it falls, the volume of air inside the cylinder decreases, so the pressure will increase. And so eventually you'll reach an equilibrium position. And I say, okay, cool. So you can draw that out. So let's say it falls to about there. Your task is to derive an expression for the height you fall through. And I'm just going to demonstrate one way in which you can do that, and some of the mistakes I would typically see. So you might start by saying, okay, let's assign some values. The piston is going to have a weight mg, and we know that there's going to be a pressure, and the force is the pressure times the area. So let's say that's the pressure times the area. And the equilibrium will be when those two forces balance out. That's actually wrong. And this is by far the most common misconception I see when it comes to this question, because almost everybody neglects the fact that there is still air above the piston. So there's also going to be this force downwards, which is the atmospheric pressure acting on the area. So in fact, there are three forces to consider. If you get that wrong in the real thing, realistically, they're not going to let you go so far down a rabbit hole just to pull you back again. They might have that conversation instead, right there, nip that in the bud, so you can keep moving forward correctly. So when do we reach equilibrium? Well, that's going to be when the downward forces are equal to the upward force. So when the pressure times the area is equal to the weight plus the gas pressure acting from above. Okay, so what we might do now is call this full height, I don't know, I'll call it x. And what we need to do is to work out what that pressure of gas is going to be inside the cylinder, underneath the piston, in terms of atmospheric pressure. And for that, bringing it back to the syllabus, I know I can use Boyle's law. So I can say that P1V1 equals P2V2, where P1 initially, let's think about the change before, it was at atmospheric pressure, and the volume would have been the full height times this area, times AX. And that's the new pressure, P, that we're trying to find, it goes to, and the new volume is the area times x minus h. So here I can see that the a's are going to cancel, and that PAX over x minus h is equal to P. Okay, so that is something I'm going to plug in here. So PAXA all over x minus h equals mg plus PAA. And we want to derive h, so I want to make h the subject of this equation. So I'm going to first, and as ever with an interview, always saying everything out loud, similar to what I'm doing now. Even if you think it's obvious, just say it. So I'm just going to rearrange things to get the h on top, and then rearrange again to get h is equal to x minus PAXA over mg plus PAA. Now, a very common thing that I see is to be satisfied that I have made h the subject of the formula and to just stop. And while technically this is mathematically true, it's not very interesting yet. We can do more to get more meaning out of this, which is something I would definitely encourage you guys to do where you can. So the first thing I see is I can take an x out. So you get 1 minus PAA over mg plus PAA. And then I can take them to the same denominator. So that would be x into getting everything over mg plus PAA. That would be mg plus PAA minus PAA. So those would cancel over mg plus PAA. And so that's actually a much better expression. So I'll just write that on the side just so I have that. So by taking the x to the outside, I can see it's just some ratio, some fraction of the total original height. And this is a much better expression. And this would be correct, but there's actually more we can do with this. Not so much in rearranging it, but we can definitely get more information out of this expression that we've just derived. We can evaluate whether it makes sense. So this makes certain predictions. What happens, for instance, as the atmospheric pressure tends to 0? Well, as the atmospheric pressure tends to 0, that term goes away. That just becomes mg over mg, which is 1. So h equals x, and it sinks right to the bottom. And this makes sense physically, because if this is done in a vacuum, there's nothing resisting the piston making it all the way to the bottom. You could also consider what happens as, for instance, the area tends to infinity. So let's say the area gets really large. What would that mean? Well, this would dominate, and you would end up getting something over infinity, which means that h would tend to 0. So in other words, for the same weight being spread out infinitely far, the actual pressure due to that weight is very small. And so it's not going, it would sort of sit on a massive cushion of air, which would resist compression. I'm not explaining that very well. So they might, in the moment, if you did something like that, they might challenge you, get you to finesse your language in the way that they like. In that case, you would adopt their language, give it back to them, and they'd be satisfied. It's not a very intuitive one, this, because we can't really make sense of it. So maybe, yeah, another way we can think about this then to make sense of a going to infinity would be, why don't we consider these two, the resultant force of PAA and PA. So we could instead replace those, I suppose, with an upwards force of delta P times A, where that pressure differential is multiplied by the area and would have to equal the weight. And so that pressure differential would be equal to the weight over the area. And so as the area gets really large, the pressure differential gets really small, which means it doesn't compress very much. So that does make sense physically as well. Another big one, why don't we consider as the mass? Because that's the one thing we really have the most control over. Maybe should have started there. What happens as the mass goes to 0? Well, then clearly we get 0 over something that's not 0. So the h would just tend to 0 in our expression. And that makes sense physically, because if we put no mass on, it's not going to drop downwards. We could consider what happens as the mass tends to infinity. Well, in that case, similar to before, in this case, we get infinity. The mg will then dominate the PAA. And so it will approximately be mg over mg, which is just 1. And again, h will tend to x, which also makes sense physically, because if we have infinite mass, it is going to drop down to the bottom. In practice, that wouldn't happen because the pressure would get so high that the cylinder would explode. But theoretically speaking, that's what it would be trying to do. So I think this is a really interesting case study for not just deriving expressions, but then probing those expressions to see if they give us anything that we can that predicts reality and evaluate how good the model is. So this is good derivation number 1. Let's consider yeah, I don't think I did this one. So this is one taken from a BFO paper. We're going to have a ramp. Where that's theta and that's theta. We're going to have a motorcyclist that's going to ride up the ramp, leave at point P, leave at point O, sorry. It's going to fly off with a speed U, and then go through the air and then land at this point P, which is a distance L down the slope. We are going to derive the time for which he is airborne as a function of that initial speed, theta, and g, so not in terms of L. This, taking it back to the syllabus, we know what topic this is. This is projectiles, and we know what to do with projectiles. You resolve vertically and horizontally, and then relate the motion. So that's exactly what I'm going to do here. I'm going to first draw a resolving triangle here, where that is theta, and say that vertically, we're going to have our suvat, where Now, very importantly, if I have to find upward as positive, it ends up lower than it started, which means S has to be negative L sine theta. That is by far the most common mistake I see. It's people saying, oh, it's just L sine theta, and not considering the direction. Vertically speaking, the upwards component of that initial speed would be u sine theta acting upwards, which means it's positive. A would be minus g, minus because it's downwards. And this is going to be t, the time we're trying to find. We also know horizontally, you'll just have distance equals speed times time, assuming that there's no air resistance. And that's another really important skill when it comes to your derivations in interview, is showing them that you're aware of what assumptions you're making. It's perfectly legitimate to make them, as long as you can justify them, or to demonstrate that if you don't think you can fully justify your assumption, you can say, okay, this might be an approximation, maybe we can refine this better down the line, but it shows that you have that awareness of your process. So assuming no air resistance, it means we can say that there's no acceleration, we just have distance equals speed times time. So the horizontal distance traveled is L cos theta. The initial horizontal component of that initial velocity is u cos theta, by considering this resulting triangle here, where that is also theta. It's also where I got my u sine theta. And again, this t is going to be equal to t. Now that's a simpler relationship to work with. We can just say that distance equals speed times time, horizontally speaking. So L cos theta is ut cos theta, multiplying those together. And the cos thetas we can divide through and say that L is equal to ut. Because this is, we don't need to consider the case where cos theta equals 0, which would be the only reason not to divide by cos theta. The reason being is because then these would both be 90 degrees. You wouldn't have a triangle. It's not a physical case in this situation. So I'm comfortable dividing through by that cos theta. So substituting that into here and using the relationship S equals ut plus half at squared, always starting from the base equation that I'm working with, not just going straight to it. Good way to make sure I demonstrate my understanding and also don't get lost. Don't like substitute anything in weird. So L is ut, so that becomes minus ut sine theta equals ut sine theta minus a half gt squared. You'll notice at this point, again, thinking about that really common mistake a lot of people make, not considering the sign of the displacement. What would happen if we'd made that positive? This would be ut sine theta equals ut sine theta minus a half gt squared. And the ut sine thetas would cancel, and you would just get half gt squared equals 0, which breaks. That's the point at which I would let people get that far and then point out something's gone wrong and get them to work out what they've done. So now that we have this as negative, though, by moving everything to one side, we get a half gt squared minus 2 ut sine theta equals 0. In this instance, I'm not going to just divide through by t. I think it's more interesting to factorize it out. We could have done the same thing over here, by the way, and said L cos theta minus ut cos theta equals 0 and factored out the cos theta. And that might have been more rigorous to then say this is solved when cos theta equals 0, which isn't physical for the situation that we've described, or when L equals ut. But doing that here is quite interesting, because we get a half gt minus 2u sine theta. And so we get the two time positions where t equals 0 or t equals 4u sine theta over g. And this is going to be our answer for the question as asked. But an interesting consideration is why this time falls out of this equation. because it's an opportunity for you to think really deeply about exactly what that equation is and exactly what that equation tells you. If you take a minute to think about that, what we've asked it to do is to find all the positions. Well, we can consider two things happening completely separately. The motorcyclist is being projected, and the slope is doing its thing. So the motorcyclist is moving, and the ground is moving underneath him. By setting s is equal to minus L sine theta, that s is the displacement of the motorcyclist. So what we're asking the equation to do is to find the vertical, it's to find the points where the vertical displacement of the motorcyclist is equal to the vertical displacement of the slope. In other words, where is the motorcyclist in contact with the slope? And the answer is obviously P, but it's also obviously O, which is why this falls out. The equation has done exactly what we have told it to do, which I think is really interesting. And instead of just discarding solutions that you know aren't the ones that are being asked for, you can dig that little bit deeper and see if you can find some meaning hidden either in that solution or in the process by which we arrived at that solution. This is also good because it's classic interview skills in that it is what I call syllabus with a twist. So you're used to doing projectiles day to day in your syllabus, but typically speaking, you haven't seen something with a ramp like that. So it just puts that little bit of a twist on it to make sure it's new enough, that it's interesting enough to give you the chance to prove a problem-solving skill as opposed to just, I've memorized this solution. Okay, so let me move from here on to another type of derivation, which requires a lot of assumptions. So this is one I quite like because it also, especially for engineers, this is one that has real-world engineering applications. So let's say I draw some sort of, I don't like how I've drawn that. Let me do it the other way. So let's say I draw a windmill. And so the windmill is going round when the wind blows on it with a speed v. And what I'd like to derive is a relationship between the power derived by the wind turbine and the speed of the wind that is going into it. And that's because flow rate, I think, is very interesting, especially for anyone going for engineering. So there are certain assumptions we're going to have to make that aren't necessarily true, but are good enough to get a rough relationship. So let's assume, first of all, that all of the air passing through the turbine gives all of its kinetic energy to the turbine. Is that realistic? Not really. There's a whole bunch of air that passes between the blades, and even the air that hits the blades is not necessarily stopped. But we can, let's say that what we can do is make that assumption, state we're making that assumption, and then understand that our relationship is dependent upon that assumption being true, and discuss how reasonable that is. So we're going to assume that. So we want the energy, obviously half mv squared. So we've got to spend some time working out what the mass is. A lot of people will say per second. My personal favorite is to think about a general time t rather than specifically for 1 second, although that will also work. So I'll kind of do this two ways, my preferred way, and then the alternative in case you prefer that. So you can consider general time t. Well, in general time t, the distance the air travels is vt, and the cross-sectional area is sort of fixed by the area of the turbine blades. So we know that the volume of air moving through the blade is A times this Vt. And because mass equals density times volume, it means the mass is the density times that volume expression. And therefore, I can plug that into the kinetic energy formula and end up with this V cubed over T. And then the power, which is the change in energy over the change in time, you divide by time, slash you differentiate with respect to time, same thing in this instance, and you would get that the power is a half times the density of air times the cross-sectional area times V cubed. In other words, we found that P is proportional to V cubed. This would also have worked if we'd considered what happens in 1 second. So in 1 second, the distance moved is V. So the volume is a V. The mass is rho a V. The kinetic energy would therefore be a half rho a V cubed. And because this is in 1 second, that is the number of joules per second, and therefore is also the power. Great. So we've got to this point where power is proportional to V cubed. The question might be, what does that mean in terms of the practical application of your wind turbine? And so there's a couple ways of thinking about that. A lot of people are very comfortable saying, well, that means as V goes up, so as V doubles, P gets multiplied by 8. So it's very sensitive to power, and if the wind is really high, you'll get a lot of power out. And that is true. But another way to think about that is the flip side. As V halves, P goes to 1/8 of its original value. And that, I think, is slightly more meaningful because that tells me if the wind drops, the power really drops. And so we might want to ensure that we have our wind turbine in a location with a very constant and predictable wind speed, which is high enough to derive meaningful power, and doesn't dip too low below that. Now, one thing that's interesting then is they can ask you something like, using your understanding of the syllabus, do you think there'd be any problem with it having a high velocity? And the reason why this is interesting is because looking at the equation, you might think, no, obviously not. You want a really high V because then you'd get really high power. You'd get a lot of energy out of your wind turbine, which is what you think you want. But where this comes into play, there is something from your syllabus you can use to help here. You know that the blades are undergoing circular motion. And so you may not be able to consider with what you know from the syllabus, like the exact way that's going to work with the center of mass of the different blades and rotational mechanics, but you do know in general that the centripetal force, if we consider just the points at the tip, we know that F equals mv squared over r for the resultant force on that point. Acting towards the center. And we know by Newton's third law, every action has an equal and opposite reaction when two objects interact. And therefore, there's a force pulling out from the center of this thing equal to mv squared over r. So we would expect the force on this place where the turbine blades attach to be proportional to v squared. And so as the wind speed increases too high, maybe that force gets too high, and in the worst case scenario, they would go flying off. You would get some sort of mechanical failure. And in practice, that is what happens. So if you're in a storm situation where the wind speed is very high, if you live anywhere near a wind farm, if you look, you'll see they actually shut them down entirely and prevent them from moving. So you actually don't get to capitalize on high wind speeds because it threatens the mechanical integrity of your wind turbine blades, which is kind of interesting. And then you might think, well, in practice, what do they do then to make them as stable as possible? And so if you're going in for engineering, you might discuss how the actual shape of the blades is not a thin line like this, but more triangular. to make them more stable because the center of mass is closer to the center of rotation for each blade, which means you actually get a little less torque required to keep it moving around. So you're able to sort of extend the length of the blade and capture more area of air without increasing too much the risk of that breaking off, because you've reduced the force, but also the force is acting on a bigger area. So you decrease the stress or the pressure there at the base of the blade, decreasing the risk of something like that happening. Is that strictly speaking exactly how that works? Not necessarily so. The purpose of an interview, though, is not to precisely solve the problem, but to demonstrate how you can apply your syllabus material to unseen problems. So does that solve wind farms? No. Is that a good application of your syllabus understanding? Absolutely. And so that feels like a good way to go about this. What other good ones do I have? Yes, let's consider a classic, which I got wrong when I sat the BFO when I was in A-level, because I had never seen the problem before. We're going to consider a sphere. And we're going to consider a particle resting on the sphere. It's in unstable equilibrium, and it starts to slide off from rest. What's going to happen? So you might say, okay, well, it's going to slide down, and eventually I know it's going to sort of fly off. It's not going to follow it all the way down. Eventually it'll fall off the sphere and then undergo sort of normal parabolic projectile motion until it hits the ground. And I say, very good. So let's find this point B where it falls off. And we're going to derive for that this angle theta at which it loses contact with the surface of the sphere. So some people get a little bit stuck here. Some people consider forces in a way that doesn't quite work. I've seen people try and use suvat in a way that doesn't quite work. But as always, they'll give you an opportunity to demonstrate what you know. So even if you're not getting it right, they'll give you a chance to explore an idea, decide for yourself whether it's working, and then walk yourself back if it's not. So there's nothing wrong with having a good go, deciding it's wrong, walking it back. It all demonstrates the process. But the actual solution path here depends on an understanding that between A and B, it will be undergoing circular motion. So we're going to have to consider the forces where here we have a reaction force, and here we have the weight mg. Here we also have the weight mg. But if this is the point where it's losing contact with the surface of the sphere, it means that that reaction force from the surface of the sphere acting on the particle must be 0. We get no r acting radially. At some point in the middle, we would get a small r with an mg. And that r will decrease to 0, and then it loses contact at B. And what do we know at B? Therefore, by angles in parallel lines, we know that this angle is also theta. And we can say F equals mv squared over r, where this F is the resultant force. And say that the resultant force acting towards the center of the circle at B is simply mg cos theta. And that will equal mv squared over r. The m's will cancel, and you get that gr cos theta equals v squared. This is the point at which you might also get stuck about where to move from here. This is certainly where I got stuck the first time I ever attempted this problem. And the context clue here is your v squared. And I'm thinking, where do I know v squared? Where does v squared come up? In general, when it comes to any engineering or physics problem, there's typically 2 schools of thought when you approach them. You're either thinking about forces or you're thinking about energy. And so if you're trying forces and forces don't work out for you anymore, energy might be the way to go. And that's the case here. Because we can see it's falling in height and gaining speed. The GPE is turning into kinetic energy. And so we can set that equation and say that the GPE loss is equal to the kinetic energy gain. So the GPE loss, we need to find that height h that it moves through. And we do that by recognizing that if that total distance from O to A is r, that this distance here is r cos theta by using simple trigonometry. And so this distance left over is r minus r cos theta. So that's the height you fall through. So it's mg delta h equals half mv squared. Again, the m's will cancel, and we get that 2gr into 1 minus cos theta is equal to v squared. Plugging that in here, we see that gr cos theta is equal to 2gr into 1 minus cos theta. The grs cancel themselves away because it's clear that neither g nor r is going to be equal to 0 in this case. I don't need to consider those options. Cos theta equals 2 minus 2 cos theta. 3 cos theta equals 2. Cos theta is 2/3. This does not have a simple solution. You do not have a calculator. This is the point at which you stop, but you're satisfied. You've reached the correct answer. And so hopefully you can see that a lot of these derivations, none of the steps is particularly difficult. Each of them just relies on some simple concept like GPE, kinetic energy, F equals mv squared over r. Lots of these things that always starts from the syllabus and ends with you gaining an understanding of this problem that you didn't have before. Another fun classic, as long as we're on the classics, is the maximum height equation. So we have a projectile being launched at an angle theta and a speed u, and we want it to go as far as possible. What is the angle at which we have to throw it in order to maximize that distance? And you're allowed to bring your common sense into interview, and so you can say, oh, well, obviously it's going to be 45 degrees. And they will say, very good, prove it. And so we'll use similar skills that we used before. For projectiles, we know we're going to have vertical, suvat, and horizontally, we know we're just going to have distance equals speed times time. Once again, making the assumption that their resistance is negligible. So vertically, we have u sine theta. A is minus g. The vertical displacement, if it's trying to land, is 0. It is the same height at which it started, so the vertical displacement is 0. And from this, we can get the height for which it is airborne from s equals ut plus a half at squared. By the way, it's while I'm here, one thing I typically notice is one way to demonstrate your skill at A level is to skip steps, get there quickly, do a lot in your head. Once you sort of hit Cambridge and once you hit a certain level at university, actually you show skill by being elegant, by not skipping this step, by stating where you're starting from and moving through all the steps in a very clean way. So it's not about speed anymore. It's about elegant working. So you're going to try specifically not to skip the steps, but just to use as few as possible. So 0 equals ut sine theta minus a half gt squared. We can take a t out. And as before, we know that t will equal 0 here at the point at which it's launched. But if we want the time, because that is where the vertical displacement is 0, but the other point at which it's 0 is this point that lands, which will be given by the second term here. So t is equal to 2u sine theta over g. And we can plug that in here to get this distance d. The horizontal component of velocity is u cos theta, and we've just derived the time as 2u sine theta over g, which means that the distance d is equal to speed times time. So we get 2u squared sine theta cos theta over g. And we recognize that 2 sine theta cos theta is equal to sine of 2 theta. So we plug that in here and find that the distance is proportional to sine of 2 theta. And we know how to maximize that. The maximum happens when sine of 2 theta is equal to 1, which from a sine graph, we know that it's 2 theta. So the period has been divided by 2. The period which was 360 is now 180. That is now 90. That maximum happens at 45 degrees, which is our final answer. Which proves what we already knew. And I think while I'm here as well, there's one idea I've been dying to test out and have purposely not done, because as you can see, a lot of these are ones I have done before. Now I want to put myself in your shoes and derive something I have never derived before. Where I think from memory, the premise of the question is, I suppose it doesn't really matter how we define the angle, but I think from memory, the idea is that the angle is defined from the vertical this time of a projectile, only this time, instead of going as far as possible along the horizontal, we want to find the minimum angle from the vertical such that the distance of the projectile from its starting position is always increasing. Now, that might not make a lot of sense. I have never tried this before, so what I'm going to do is to think about why there should be a minimum theta. So I'm going to tell myself, okay, what if theta was 0? It would clearly go up, it would reach its maximum height, but then it would come back down and start getting closer to the start point again, and then land back at its start point. So when theta equals 0, the displacement time graph will go up and then come back down to 0 again. So not even displacement, distance time graph. Displacement? No, it is displacement time graph. I lie. In this case, there's not really that... There's not much of a difference in this specific example. It's going to matter when we start including the horizontal component. So we can, what we want is where the distance is always increasing, and we can see after it's reached its max height, it's going to come back down to 0. So now let's think about, okay, well, now we're going to do theta not equal to 0. So we're going to increase it, and at some point this will always increase. But obviously, once we increase theta from 0, we now introduce a horizontal component. So let's think about what that would be. We are going to do our vertical and our horizontal again. All the same assumptions as before. It's going to start at, in this case, u cos theta will be the vertical component. Let's say this is time t. I think t will be relevant. And I know s will be relevant. Here is u sine theta acting horizontally, where time t equals t again. So for at a time t equals t, let's work out what the sort of coordinates of that point would be. Well, here distance equals speed times time. So that is our effective x coordinate of this point. And the y coordinate of this point, s equals ut plus half at squared. A Come on, Ben. Half AT squared. Obey me. Right. S equals UT cos theta minus half GT squared. And that is the, okay, that's the y coordinate of that point. So the distance, if we use Pythagoras, the distance of that particle from the start point, distance squared, is equal to this, is equal to the y squared plus the x squared. So u squared t squared cos squared theta minus twice the middle two, which will cancel the half. So u g t squared cos theta, slowing down so I don't make an execution error, plus a quarter g squared t squared plus u squared t squared sine squared theta is the distance. I can see immediately I have a cos squared and a sine squared. And cos squared plus sine squared is 1. So these will just add to u squared t squared minus ug t squared cos theta plus a quarter g squared t squared. I can clearly factorize out a t squared from this. And we want this to be, actually, what I'll do is I will immediately say, I think I can immediately take the differential of this. It may not be the most efficient, but again, this is a live solve. Now, the logic here is I want the distance to always be increasing with time. So I want this to always, so that means the distance squared is also always increasing with time. So if I differentiate with respect to time, this should always be positive. So if I differentiate this, I get 2u squared t minus 2u gt cos theta plus a half g squared t, which needs to always be bigger than 0. So for all time, in fact, if I take a half t out, I'll be left with 4u squared minus 4ug cos theta plus g squared. Ah, does this turn into anything interesting? Well, t is always positive, positive, positive. So we need this thing in the bracket to always be positive. So let me isolate that idea. So we now need 4u squared minus 4ug cos theta plus g squared to be bigger than 0. I can add this across to the other side. 4ug cos theta. And because u is positive and g is positive, I can divide through by 4ug without having to worry about changing the sign here. Does this feel like it should be universal enough not to rely on u, though? Wait, no, I've done it also. Hold on a minute. That cos theta just shouldn't be there. I suppose this does get interesting if I split it back out, because then I get a u over g plus g over 4u, which just sort of looks fun. Is there anything more meaningful I can get out of this? Why should it depend on you? It doesn't feel like it should depend on you. Also, would this be unitless? Something feels off. Let me just evaluate whether, let's see, ut plus a half at. Oh, I'm an idiot. No. Ah. Okay, in an actual interview, if you made a silly execution error like that, they would have spotted it much earlier. All right. Apologies. Okay, but I found it. And that's the point. Ut plus half at squared. I forgot to put the square in before I squared the whole thing up. So that has ruined everything. I need to go right back to here. Okay, so not to worry because I have demonstrated my ability to find the mistake and then correct the mistake. And let's get rid of all of you. Okay, it's fine. Take 2. U squared, T squared. And now, by the way, look how unfazed I am. Like, it's fine. People make mistakes. You catch the mistakes, you're fine. Don't let this be the sort of thing that puts you off. They don't think execution errors are like the worst thing in the world. It's just a small blip. They evaluate you on the substance of your work, not whether something small like that goes wrong. So unbothered, unfazed. Let's keep going. Plus a quarter GT4 plus U squared T squared sine squared theta. And then this, as before, would just give you this. Now, by the way, one skill that I demonstrated there that I was quite pleased with was the ability to feel that something was just off. We were getting cos theta, which we know is a unitless dimension, and yet we were getting U squared plus G squared on the top, which is very much not units that combine, and a UG on the bottom. Like, the units weren't working out. So it just felt like something was wrong, which is why I went back to check. Okay, now we have this thing, and this thing should always be positive when I differentiate it. So if I differentiate this, I get 2u squared t minus 3ut squared g cos theta plus gt cubed, which must always be bigger than 0. So that's a cubic in t. That becomes t into gt squared minus 3ug cos theta, lots of t, plus 2u squared. Okay. This is a cubic, so I'm going to try and find the solutions. What would be the solutions to this quadratic in t? Oh, it nearly factorizes, you know. Which is so frustrating. Let's just try and plug that into the quadratic because I know I've got a skill. So even if I don't know it's going to work, I'm going to demonstrate the skill. So I would solve for t. Obviously, we have t equals 0 from this part if I'm trying to sketch it. Now from this guy, we would get t equals minus b plus or minus square root b squared minus 4ac all over 2a. G cos theta plus or minus, let me see if I can tidy this up now. Minus 8u squared g all over 2g. It's definitely... Let me just check my units again. So distance equals speed times time. Yeah, those units cancels the time. That cancels the time. Yeah, these units work. These units definitely work. We just check everything's gone okay. Yeah. The problem is I just don't like this cubic. Oh no, wait. Wrong. Okay, I don't like this method. Let's try something else. Because I've just had a thought, rather than generalizing it like that, what I could do is to say what would need to be true such that this thing is always positive. Well, what does it mean for, well, for all positive, for all t being bigger than 0? Well, what that would mean is that, yes, there's this crossing point at t equals 0, but it means that this thing actually would have no solutions. Or, put another way, we would need to find the turning point of this and say that this maximum point has to be above the x-axis and this minimum point has to also be above the x-axis. So it would certainly, I'm going to do it both ways just for proof of concept. So one way of doing it would be to say that this thing has no real solutions, which means the discriminant is less than 0. So the discriminant is found by that squared, which is 9u squared g squared cos. Hey, nope, I am illiterate. Let me try again. So it's 9u squared g squared cos squared theta. So b squared minus 4ac would have to be less than 0 in order for this thing to have no solutions, for it to never dip negative. So 9u squared g squared cos squared theta minus 8gu squared less than 0. I can happily divide by both. Well, I'll just factorize them out. Why not? Let's factorize out a ug. 9ug cos squared theta minus 8u would need to be negative, which means that u is positive, u is positive. It means that this term would therefore have to be negative. Positive times negative is negative, which means that by moving that across, 9u, sorry, that should have been a u squared I factorized out. Yes, which means that cos squared theta must be less than 8 over 9g. And in this, so now what I'm doing is I'm thinking about ranges. So I think theta will have to be between 0 and 90 degrees. So it will be in the region where cos theta is positive. So cos theta can never be negative. And then you can square root that and you get 2 root 2 all over 3 root g. So I think that would give you a cos theta, which is independent of u, which would give you your tipping point. So this tipping point would be at this point here, when the discriminant would be perfectly equal to 0. When the discriminant equals 0, as we found the limiting cos theta for which the distance is always increasing from the origin. I'm pleased with that. Let me see if I can do it from the other way. So if I have this cubic always needing to be positive, then this minimum point must be above the x-axis, which means if we differentiate this thing with respect to t, we'll just see if this would have been faster. 6ut g cos theta plus 3gt squared, this thing, we can set that equal to 0 to find where this minimum point is. So it's a quadratic, so we're going to get 2 times, obviously. So solving for t equals minus b plus or minus square root of b squared minus 4 times that minus 4. Let me move it over. For a c all over 2a. No, okay, that's just not going to be it, because then to find The solution to plug it back in to say that thing would have to be bigger than 0. Yeah, that's not going to be it. So it's going to be done this way. Certainly. I think this is the solution. Okay. I'm pleased with that anyway. I think that gets it. I think that, or rather the limiting, yeah, so theta would have to be bigger than inverse cos of 2/3 root of g over 2, something like that. Obviously, I could rationalize the denominator, but like, bleh. So I think that's the solution. I don't know that's correct. And I really can't be bothered to chat GPT it or look it up. I'm going to run this past a student who I know has solved this, and if it's desperately wrong, I think I'll update it in the comment section. But remember, this is not necessarily about knowing the correct answer. This is about demonstrating the correct process. Because in the real thing, you're going to have an interviewer there who's going to be able to pick you up if you've done something silly that's going to waste a lot of time. So at this point now, where I'd be wanting to ask ChatGPT if I was correct, this is the point where an interviewer would ask you if you were correct. But I think that the point still stands. I got something wrong in this, but I didn't let it phase me. I went back, I corrected it, and I got to a correct solution. And this is showing how to walk through your steps to gain understanding that you didn't have before. So that's about an hour. I think that's a good place to stop. I don't think there's anything desperately important that I've needed to have gone through. So yeah, we'll stop there. Let me just give a little bit of a debrief. So remembering that this is a lesson, not a test, this is you demonstrating that you can bring what you've already learned from your syllabus, apply it to a new problem, and learn something new. So we went through some of the questions where we derived expressions and then made predictions based on what those expressions gave us and evaluated whether those were realistic or not. We also thought about the assumptions that we were using in our derivations and how they might have impacted our results. We thought about forces and energy and all the different types of things that we can use to solve problems like this. And I showed you a more complex problem that might be harder than something you would get in the real thing, but that shows you what it's like for me to see something I've never seen before, and you see the ways I kind of backtrack on myself and then find the right solution. Because it's not about getting there instantly correctly. It's about doing enough to convince them that you would be fine on your own. That you could test things out, use your gut sense to see, oh, is this right? That's why we evaluated whether these calculations actually yielded good results. Because that's something I'm thinking about all the time. That's how I spotted my mistake. I went, these units aren't working. This feels wrong, which is why I went back, looked for a mistake that I thought I would find, did find it, corrected it, got it right in the end. Those are the sorts of make or break moments in an interview that make them go, you're going to be just fine. You can come on in, you'll be fine in the system. So hopefully you've gained from that. Hopefully you found that fun. As always, leave comments if you think there's a particular derivation you want me to do or a different type of question you want me to demonstrate when it comes to interview prep. I'd be happy to cover those. But in the meantime, keep working hard at it. Work hard. Have fun. I'll see you guys next time.